This is Jenks basically power station. This is actually across the river from where I live in South Tulsa. And that's basically how we generate energy. We put the natural gas, we make big fire, and that big fire make water, steam, turn water into steam, and then we use the steam to we use the water to generate steam in the boiler, and once the steam is generated, you use it to turn a turbine, and then condense, pump again, and so on and so forth. And of course, this cycle is called the Rankine cycle, and you have probably seen it before many times, right? And recently, and this what fueled the industrial revolution, basically, not steam power. But recently, people started worried about the CO2 emission, and they start basically thinking, well, are we burning too much? Are we changing the climate by putting too much CO2? So whether the CO2 is changing the planet climate or not, that's the controversial part, right? People would say, no, we are not. Yes, we are. But the fact that we are burning so much CO2 and the CO2 level is way higher than what it was before, there is no denying this. Just look at the record of the CO2 in the atmosphere. So definitely we are putting so much CO2, right? So as mechanical engineer, whether this is hurting the planet or not, but it doesn't matter. Our job is like, no, we shouldn't put this much CO2 in the atmosphere. We should keep the planet as it is. Why we want to change it? As good as it is. So that's why there is a lot of inventions and technology development and finding another way to turn that turbine. How we can turn that turbine without burning stuff, or how we can turn this turbine with burning clean stuff, right? So in the next few charts, you will see the US energy, okay, production and consumption. So this is 2019. This is the last one that they produced. And you can see how the petroleum, how much, like the thickness of the bar is how much? 36 petroleum, coal is 11, natural gas is 32, and geothermal, wind, hydro, nuclear, and solar are so tiny. Look at this. And actually, nuclear this year marked the largest retirement ever of the nuclear power plants. They are shutting down 2 power plants, big power plants. So what I'm trying to say is that when you look at this, most of the energy comes from burning natural gas and petroleum. And where do we spend all that energy? First, big chunk of those things go to electricity, and then that electricity go residential, commercial, industrial, and transportation. You can see like 25, 9, right? And surprisingly, 67% is rejected energy. And that's shocking. Like, so you're burning all that heat, and 67% you send it to the atmosphere. When you think about that Jenks power plant that I told you, what do you think the efficiency of this plant is? Give me an estimate. Give me a number. What do you think the efficiency? Oh,
30%.
40%. 40% more or less. The 60% is the one in Owasso. The power plant in Owasso is like 65%. What's the difference? One of them is combined cycle and built recently. The one in Jenks was really old and is basically just like a simple steam cycle. Okay, so what does it mean 40%? It means that when they burn one joule, not, let's make 10 joule. If they burn 10 joule of natural gas, 6 joule go to the stack, right? Go out in the stack and go into the cooling tower, into the air. So you're just making a big thermal bubble to heat Tulsa can. And only 4%, only 4 out of those 10 make it as electricity into the wire. Right? So as mechanical engineer, our job is to improve those efficiency, right? Find way not to waste that much, and find way to generate that energy to start with like a cleaner method, right? And so interesting, if you compare the 2019 with say 2017, you will see, you compare those two charts. I wish I can put them side to side, but you will see how solar improved a little bit. Huh? Solar 1.04, wind 7.2.74. We see here wind is 2.35 and solar 0.775. So you can see how wind and solar are creeping up. But how much are they? Tiny thing, little, right? Very little. And you will also see how the coal is continuously decreasing. Why continuously decreasing? No, you wish. No, they are. It's decreasing because it's so expensive compared to natural gas. So natural gas is winning just because it's cheaper. So if you work for Genzinc over here, they actually sell a lot of burner for power plant that want to convert from coal to natural gas. That big burner, that big furnace, that you burn in. If you want to switch from coal to natural gas, you have to change your burners, the way you feed the fuel to the furnace. So market eventually will drive the technology in the right way, right? And that's why interesting also, it's kind of also a little bit disappointing when you look at 2016 and 2015, 2011, all those times you will see how the improvement in wind and solar is not that impressive, but there is improvement, right? And the reduction in the coal, you can see it all over. The trend is very clear to your eye. Okay. And this is again the Rankine cycle, the workhorse of all thermal conversion. Thermal conversion, what does it mean, thermal conversion? You are basically generating heat, and that heat you are trying to turn it into mechanical work on the shaft. Okay, so that conversion is limited by what's the maximum efficiency. If I give you 100 joule and I'm telling you I want this to be 100% mechanical power, you will tell me you are crazy. We cannot do this. Why? Who will say no, you can't? Who said that any thermal conversion has to be less than 100%? There is a maximum that you second law of thermodynamics, and which translate quantitatively into the Carnot cycle efficiency. 1 minus TL over TH. Right? So 1 minus TL over TH, eta Carnot is 1 minus TL over TH, where TL and TH are in Kelvin. Right? So what is TL and TH? TH would be the temperature of the furnace over here. And what's TL? TL would be the temperature of the river that you are dumping the heat to, or the temperature of the air that the cooling tower is cooling to. Okay, so I wish you can break the second law of thermodynamics. And I know people that spend 10 years of their life trying to break the second law, finding a gap in it, but they couldn't. But basically, that is the limit of thermal engine, a thermal power plant that take heat and turn into work is limited by that symbol. Okay, very good. But still, like, so the fact that Jenks is 40% and UASU is 65%, that tell you that the Carnot cycle for those power plants is probably like 75%. And that's why UASU was so close, right? So what I'm saying is that there is room to improve. I mean, Carnot cycle is not our limit. We are not even there yet. And so in order to really get really close, that is how a power plant will look like. Huh? So that cartoon, with one turbine, one boiler, one condenser, one, no, it's actually look like this. Okay, and why all this? They are trying, all this is an attempt to approach the Carnot cycle. What do you mean the Carnot cycle? Well, on a TS diagram, the Carnot cycle look like this. That beautiful square. Okay, and in that beautiful square, this area over here is work net. Okay, and that area under him is Q rejected. And so obviously you add the two of them together and you get QH. QH is work plus Q load. Right? Why? Why? Because when I apply the first law of thermodynamics, not the second law, just the first law, which basically my daughter actually picked this amazing color. Switch to grown-up color. So when you look to that heat engine, you'll find out that you are giving him QH, right? And he is producing some work, and then the rest is gonna go to the condenser or the heat pump or the chimney or whatever, kilo. So from the first law of thermodynamics, if you put like a boundary like this and say, this is my control volume, it's very clear that QH is W plus QL. Make sense? QH is W plus QL. And the efficiency is work over QH. Or simply 1 minus QL over QH. Okay? So this is for any cycle. For any cycle, the efficiency is work net. This should be work net, right? Why work net? Because there is work pump and there's work turbine. And work net is really what you get at the end of the day. So if the pump takes some work and the turbine give you some work, the difference is what you really benefit from, right? So this is for any cycle, okay? Now for the Carnot cycle specifically, it ends up being like this. And so that QL would be T delta S TL and this TH delta S, where this is delta S. Okay, so it's the area of a rectangle basically. So this is
Dr. Salam, I have a quick question.
Yes, please.
Is the ratio of TL and TH equivalent to the ratio of QL and QH?
So only for Carnot cycle, TH and TL is exactly that issue. Why? Because QL is TL delta S and QH is TH delta S. So when you cancel this, and why could I cancel them? Because that delta S is the same exactly as this. Because the cycle is look like a rectangle. So then that's why it become 1 minus TL over TH. Okay, again, just for Carnot cycle because it look like a rectangle. But if the cycle actually look like this, if the cycle look like this, or look like this, for example, so this is a Rankine cycle with a reheat, or it has some feed water heater and it actually go like this. It's not really a rectangle, and so the equation for eta efficiency is not 1 minus TL over TH. The equation instead would be always work net over Q added. And you have to figure out what is Q added. Do you add heat here and do you add heat in the reheat? And what's work net? Is it this part and this part and this part minus this pump and minus this pump? You do all the math and you will be able to calculate this. So this is always correct. And this is a special case only for beta Carnot. Make sense? So the point I'm trying to make is that all this modification of the Carnot cycle in order to turn that shape and this shape into hopefully what? A rectangle. That's what they are trying to do. Okay. When you also think about the Brayton cycle, the one that basically run gas turbine, it looks like this. Compressor, heat addition, this is again what? TS diagram. And this is V equal constant, and this is V equal constant. So what they try to do is, with reheat and with intercooling, they are, and sometimes when the cycle is actually like this, they will say, well, why can't we have like this guy will heat this guy with a heat exchange in the middle. So all those attempt is trying to approach the mechanism. All right.
So we can say in Carnot cycle, the change in entropy, entropies are same. Is that correct?
Yes, because again, look at this line and this line. And entropy in what? The entropy in the heat addition process and the heat rejection process. Right?
Thank you.
You're welcome. So when you look at this sketch, you shouldn't be surprised why they have so many feed water heaters and why they have so many turbines, because they are trying to make the cycle efficiency get as high as they can. All right? So one of the amazing things, kind of like our blessing and our curse at the same time, is that in the USA, we are fortunate to have a lot of coal and natural gas and oil. So other countries don't have that choice. Like France. France is the second country in the world with nuclear energy. Why? Because they don't have we are the first country in nuclear energy, and France is the second one. But Japan, they don't have oil and natural gas and coal that we have. So because the oil and natural gas is so cheap and so abundant, that's why we are not all driving electric cars, right? And probably my next car is gonna be a pickup truck because it's like $2 per gallon, and I would like to have my kids' bikes on the back of my truck, and then we can go somewhere, right? So we are fortunate to have all the things, but that doesn't mean that we should put so much CO2 in the atmosphere. We must find a way to actually fix it. This is the natural gas, and a bunch of you may know that in Tulsa, actually, they have the control room for the gas pipelines in the USA. Somewhere in Tulsa, they actually have the control room for a lot of natural gas pipelines. So again, we are blessed with so much natural gas. And natural gas is way better than coal when it's coming to CO2. Because when you compare coal, which is roughly can be approximately a C, and you compare natural gas, which can be roughly approximately a CH4, it's obvious that when you burn CH4, you get a lot of energy from the H4. But when you burn just carbon, C, everything will turn into CO2, right? So for the same, say 1 kilowatt hour that you produce from coal, you'll get way CO2 released than 1 kilowatt hour that you'll get from natural gas. Of course, if you burn nuclear fuel in a nuclear reactor, you get 0 CO2. Because nuclear energy does not produce CO2, for example. Okay, biomass, there's actually a bunch of professors in Stillwater that make research on how we turn switch grass and different kinds of grass into fuel. Okay, so how we can turn biomass into fuel. All right. So that's also kind of renewable source of energy, right? And you'd actually think that maybe it's kind of CO2 neutral, kind of, because those grass took CO2 from the atmosphere to form them. So when you burn them, it's like not as bad as let's get natural gas and oil from the ground and burn it, right? So burning also garbage and turning it into energy. That's very popular in the East Coast. Why? Because they don't have, in the East Coast, land is very expensive and they don't have place to dump their trash. So the only way is to basically burn it, and then that energy coming from burning those garbage and stuff can actually generate energy. And amazingly, in Tulsa, Oklahoma, we have one of those, and it just across the bridge from this campus. And it was built by Senator Inhofe when he was the mayor of Tulsa. So Senator Inhofe built that plant because at that time there was no fields basically to put the garbage in. And so Tulsa was basically where we can put all this garbage. You have to burn it. You have to make a profit for that. And we visited it last time, just like 2 years ago. I'm not sure we can visit it this year or not. But amazingly, it smells so good. You think it smells so horrible, but it smells so fruity. I guess they were burning like some kind of fruit at that time. And the guy there told us we actually burned sometimes like clothes and like and for like really strange reason. Like sometimes the jeans are defective and the company wouldn't put it in the store because it's like hurt their brand. So they rather give it to us to burn it. So like all weird stuff can basically get burned in order to generate energy. Right? So the green is biomass, the blue is hydroelectric, and you can see the wind and the solar over the year. Okay, so there's a reason why the hydroelectric is kind of limited because it's like where you can find more rivers to build them on, right? But biomass, wind, and solar, we are still at the huh, at the early stage of them, and they are peaking up, especially all over the world too, right? So they are peaking, huh? And that trend is up, and you will probably in your career, 30 years from now, you'll probably find a lot of jobs in that sector as they grow. Okay, so so in this course, we're gonna study all those kind of energy conversion methods, huh? And we will see what is the limitation of each one of them, what the and how we can improve it. So nuclear energy, those are all the nuclear reactors that we have in the USA, right? So we have a lot. We are the largest country with nuclear reactors. And although this year is the largest retirement of nuclear reactor, also this year they are starting a completely new nuclear reactor, the first one in so many years, maybe 50 years. Like it's amazing that we didn't build a new nuclear reactor for so long. But they are building one. They are building one despite the fact in Germany, like this is Fukushima accident. Those are the four reactors that exploded, and they actually made by GE, by the way, or own GE. So we will talk why did it happen and can we make a safe reactor? I once was listening to the radio and one guy on the NPR was saying why wouldn't engineers admit that nuclear reactors are not safe by default and every single nuclear reactor is an accident waiting to happen. And that was so offensive to me as engineer. Like that basically means you cannot design safe in like reactors. Of course we can, right? And actually, that one that they are building this year is inherently safe. Okay, so we will understand what does this mean. How can we make a reactor that's inherently safe, that nothing bad will happen? Is that possible? Yes, it is, and they are actually building it. This is called solar thermal. So unlike the photovoltaic panel that you just put on top of your roof and you get electricity, pump it into batteries, this one is just like the Jinx power plant, except that rather than making this big fire with uh, burning natural gas, you make the big fire or the big heat by almost mirrors. Okay, how many mirrors? You would calculate this. How many mirrors you need? How much area do you need in order to do what? In order to turn. You see how the furnace is super white? Why it's super white? Because it's super hot, right? Super hot. This is super hot to the extent that any bird crossing the ray, you get chicken, fried chicken immediately, like that. And that's why actually environmental group don't like those power plants. And they are basically like camping near them and they are watching so that they can make lawsuit against like killing birds. Right? But this then just become a ranking cycle. You have big furnace, huh? But when the temperature is that hot, and also because the sun kind of disappear after sunset, it's not the typical ranking cycle. You actually, rather than sending water, you send molten salt, okay, that you can get heated. And then you use that molten salt down in like 2 tanks over here. That's where those tanks have the molten salt and they stay hot even after sunset, okay? So fortunately, we have also the largest thermal power plant in the world. Other countries, especially in North Africa, like Morocco, they are trying to beat us to this number one position, but we have the number one position so far. Okay. It's photovoltaic. So, it's really a big deal for a lot of countries because, again, like Germany, some countries don't have the luxury of having natural gas. And they have Germany is borrowing it or buying it from Soviet Union, not Soviet Russia, no, with all the political headache that associated with this. So they have natural gas from Russia or nuclear power plant to get energy. And when the Japan accident happened, they basically just panicked. And I guess the Green Party there is so strong politically or something, but or people are they just panicked and they said no more power plants and no more nuclear power plants in Germany. You're gonna retire every one of them. So how are you gonna get your energy? Solar and wind. And so in that year after they made that decision, Germany became the largest country to install solar photovoltaic panels basically in that year. And that's amazing because when you look at how much radiation do they get, solar radiation, they get the same solar radiation like Alaska, not Arizona and New Mexico, right? I mean, the number is so low, as you will see when you study this. But what I'm trying to say is that sometimes politics change the price. So, for example, I think the largest photovoltaic field is actually in Canada, in China. How is that possible? Not in New Mexico, Arizona, or because over there, I guess you get subsidized for putting them and the tax, some kind of tax incentive that the company really can make money by actually installing it over there. Okay, but the energy is that sensitive. Like I know one. This is the chart will show you. This is Germany radiation. This is Alaska radiation level. You can see how they are purple, huh? And you can see how Arizona and New Mexico are super red, right? Also Nevada and California came out. And we are here in Oklahoma. How come we are not as hot radiation wise like New Mexico and Arizona, and we are the same latitude. Why? Why we are not getting as much radiation like them? Why, Kristen? It's more cloud. We get more cloud, more rain. That basically we don't get the sunshine that they get there. So they have more clear sky. So radiation year long, basically, right? So of course, wind energy, right, and hydropower. And so when we talk about the limitation of those techniques, you realize that you think hydro and wind as green as possible. Like people would love them, especially green environmental group. They would love solar, they would love wind and hydro. But no, they have their own problems. Wind energy kills birds, especially bats. I guess the bats see the space between the like clear, let's go, and you get chopped the moment you cross because this thing is rotating so fast. But there are research done to scare bats away from the being chopped. And hydro also, you think hydro is super uh, green, but no, those dams that they built with the turbine will prevent fish from crossing, right? And so they have like some kind of elevator. They design elevators so that the salmon and stuff they can actually take the elevator to jump across the dam to go with the. So there are engineering solutions for those problems, right? Big dams also can generate earthquakes. I'm talking about like gigawatt, 9 or 5 gigawatt. The one that they are building in Africa right now in Ethiopia. There is big scare that that dam would cause earthquake nearby. Also, it clogged the mud from moving, and usually that mud is responsible for fertilization in the downstream. So when you put a dam, the downstream don't get the mud and the plants will die. So then you have to artificially fertilize the land. And so that artificial fertilization gives you a problem if you are not being careful and taking the right fertilization, right? So every one of those techniques has his own problem, right? Nothing, there is no silver bullet, basically. This is the wind distribution. And again, we are really lucky, right? Because of that tornado alley, right? Also a wind alley, wind energy alley, right? And let's see what actually BSO, they wanted to build a huge wind farm in that region. And they're gonna make, of course, BSO doesn't build wind energy because they love environment. A company builds wind farms because they can make money over it, right? And so, but the in order to turn this power, in order to pass this power to the
Did we just have a break?
Yes, we had 15 minutes break, but it was not my choice. My laptop decided to run out of charge, and so
I
so
was waiting, and then like nothing was happening. Okay.
I'm really sorry. But it was a good break anyway. We spent the time resting while the computer was updating. All right, so I think we should start again. So we finished at this slide. We were saying how we are really lucky because of that region, right? All that wind energy available for us, all that purple. That's why I was telling you that PSO actually was trying to build a big farm, huge farm in uh, in the Panhandle of Oklahoma, because they're gonna make money out of it. And actually, if you go to any of their, they already have wind turbines. And if you go to their power plant, they have one across also the gathering place across the river. You go there in the control room, and you'll be able to see the production from the wind turbine. And they get frustrated when the wind turbine run before people woke up. They say like just like 5 o'clock in the morning, all of them were running and we had too much electricity, and now people start woke up and they want to turn the house and the coffee and everything, and the wind is not there anymore. So that's the frustration of the wind energy, right? Because it's not matching the demand. You cannot. That's actually the frustration also with solar, because the solar is in the morning, and then what happened at night? You need storage, right? That's also our problem as mechanical engineer. So the solution shouldn't really just think, you should always think no battery and we have to wait for Elon Musk to come up with his very cheap battery so that we can put in every single house. No, mechanical engineer actually have a job. And last, not 2020, but 2019, I was in the SME conference, the American Society of Mechanical Engineer. They have a conference every year where they brought like people from industry, academia, and everything. And the guest speaker was Secretary Cho. He was uh, he was Secretary of Energy under President Obama. And the guy, he will now, after he finished, he worked now in back to his research. He had Nobel Prize, if you remember. And so this guy was basically saying the solution for energy storage, he think in the future would be hydropower. What is hydropower storage? A turbine and a pump connected to each other. And when you have extra energy, because the turbines are running, no wind energy is running, no one is using electricity, you take this electric energy into the pump. The pump take the water up, store it, and then when people need the power, right, and there is no wind, what do? You reverse the water, you let it go down into the turbine, right? And amazingly, the company that provide energy from you here in Oklahoma, PSO, that's how they store their energy. They have some lake, I forgot whether it's in Pennsylvania or West Virginia or somewhere over there, where they have actually a lake up and they store the energy back and down. So it's a big network. So they actually tell me over here, like if they do anything with the power plant, they get a phone call from Ohio. That's where their control room is. And the engineers there, are you doing something with that valve? Because they are controlling the power plant from Ohio or whatever the headquarters is. Right? So those big companies basically have network of power plants and energy storage and wind portfolio. Anyway, so they were trying to build a huge farm in the Panhandle, but they just didn't get the land permit to run the cables, taking the energy from where it's generated to where it is consumed. Okay, so and why they didn't get the permit, that's a big debate, and whether people are just don't like wind farm because they are interested in, they are supporting more gas and oil, or whether it's more than this. But the point is, there is more than just the efficiency of the machines. There is environment, there is the political society environment. Like in Germany, why did they just abandon nuclear energy? Although it could be safe. It's just that the climate and the people is no more nuclear energy. We are done. We don't want to face what Japan did. And why did Japan had, you think society that's so advanced technologically, why would it have an accident? There is reason, and we will talk about this. Okay, and it's not our opinion. This is also like it's an official report made by the Japanese government. Why did they have this accident? You'll be surprised. Why? This is the wind, but offshore. If you just put the wind turbine a little bit in the water, you get more higher velocity than this. So we are so happy with this. Well, just go to the shore and you will see. And the USA finally had its first offshore farm. Okay, of course, in Denmark and Germany, they already had this so many years ago. And of course, it's useful because, or more efficient because the flat surface of the ocean. It's bad because people don't like the scenery. Although I don't really get it. I think a wind turbine is so beautiful, actually. I think it's more beautiful than the ocean itself. Like, what is so beautiful about a bunch of waves that are not, like, I mean, if they come sinusoidally, that would be beautiful. You know, it's like perfectly sinusoidal, but like completely random wave, why is that beautiful? I don't get it. I think if we just plant wind turbine all over the ocean, that would be so pretty, and they can color it if they don't like white. You know, you can give them. Anyway, seriously, people don't like, for a strange reason, they don't like wind farm in the beach. So geothermal, okay, that's basically you dig to the ground, you get hot water coming up, and that hot water you can generate energy with it. Okay, this is in Iceland. Iceland have almost 100% of their energy, 100% almost, huh? It's like 90 something, from hydro and geothermal. So those people are living for free, right? They don't have to buy natural gas or oil, and still they bankrupt their government. At one point, Iceland actually declared bankruptcy. So all those kind of energy, and we will talk about more invention and more way, those are all available for us. And the problem is, most of the time, besides environment, is the price, competitiveness, economically. And this chart came from a financial report, not even engineer, but just financial, compared the price of generating energy from down there over here. That's gas combined cycle. That's Oahu. Okay, that's the Oahu power plant. Jinx would be like here. But Oahu power plant is here, and when you go up and you see what is the price of wind is here, and solar is here. So the point is, solar and wind are becoming more competitive financially. And that's why a company like this all wanted to build a wind farm rather than building a new power plant that run natural gas or coal. They know that they will make money building it out of, or basically generating electricity from wind and solar energy. So the future is here. Okay, we are not gonna wait too long before we see this. The only problem that we need to, hopefully one of you will come up with an invention for how to efficiently store energy. Okay, because again, the mismatch between the production, right? The production of, say, solar and the consumption of humans. Okay, also, this is not just for solar and wind. Energy storage is always required because a lot of power plants, like nuclear, for example, and even the gas power plant like the one in Jinx, they don't like to run in partial load. The efficiency drop when you don't run it at full design condition, the efficiency actually drop. So they rather run 100% all the time. Okay. So what do you do with the energy? Again, you store it in somehow. Okay, and so we will talk about those energy storage. And specifically, or one of the attractive one is, of course, electric transportation, because not only because they don't generate CO2 on the road, but also because being charged at night while you are sleeping can be a really good place to store that extra energy that the nuclear power plant is actually generating and no one is using, right? So it will be a perfect combination. This is just like 2 slides about our policy in the class. So you are encouraged to ask as many questions as you can, both for those in class and both online. And I always say there is no stupid question. Any question that you have in mind is probably a really good question, because probably I said it very quickly, or probably it's very complicated that it requires me to teach it again. So you will do everyone a favor by just raising your hand and ask me the question. Okay. Of course, people online, sometimes I don't see your hand because I'm not monitoring the chat. So people online, you have the permission, I guess, to ask. And if it's just run out of control, I will let you know. But feel free to interrupt me. And even if you think your question is stupid, and even if you think that you probably just didn't get it, because it's only you and everyone else get it, you will still do us a favor by asking that question. Why? Because one, it might not really be stupid or anything. You are just thinking that. And two, even if it's stupid, you give me a chance to get a rest and listen to you and stop talking. Third, you'll make everyone feel good about themselves. You think, you're so smart. He's the only one that don't get it. So anyway, we will really appreciate any question that you ask, even if you think it's not a good question. But chances are it is a good question, and all questions are good. Okay, so raise your question anytime, raise your hand anytime you have a question. We talked about the late policy. So this part, we talked about, hopefully I did scare you about cheating and copying from each other. Hopefully, right? And hopefully this year I will not get as many people copying like every year. But at the same time, I would like to really encourage you to work with each other. Okay? So this is very, very helpful. Even if you already know the solution for everything and you don't need help, it's really helpful for you to help your friend or your colleague that actually does not know the solution. Because understanding the topic is one thing, but explaining it to other people is another level. Because that person will ask you, like he will probe you with really good questions. And those questions will allow you to revise the material in your head and trying to figure out, yeah, why? You know, you will ask a lot of why. And when you ask a lot of why, you will learn the material really good. Okay? So the only difference is that when you work with each other, does this mean that like we drive the same homework with the same number? Or can we just work together and you wanted a chart, here's a chart and copy of it, and another copy of it, because we all work together. 1 year, 3 of my best guys, 4 actually, they just give me 1 color chart and 3 black and white charts. And so the TA told me, well, those people did copy from each other. I looked to the charts and yes, they are carbon copy. So I got the 4 of them. I said, why? And they said, well, we work together. I said, like, how? How did you write this program together? Like, he said, one was typing and the 3 were around him and we were like helping each other to write. That's not acceptable. Not acceptable. You cannot produce the same product and say we all worked on this together. So what does it mean then to work together if we are not gonna produce the same product. It means that you discuss with each other. How did you do it? What's the right equation? You can even ask the guy, well, what did you get for the final answer? And he will tell you, well, I got 50, or I got 50 by 50%. And then you will tell him, well, I got 47. And he will tell you, like, why? Show me the solution. And you can show him the solution. Huh? And look, here's what I did. Ah, you actually use the wrong pressure. It's actually lower. Why? And you can discuss. But under no circumstances they will ever come exactly the same. And they will not even come in the same order when you are talking to each other. But if you have a paper in front of you and he is writing and then you are writing like him, that's not working together. That's basically copying from him. So please understand the difference. And if you are ever confused, ask me, and talk to me and tell me, well, we are planning to do this. Is that okay or not? And then I can explain to you which is okay and which is not. All right? But by all means, having a study group or working together or like just discussing how things are done is really, really beneficial for both sides. Okay? Very good. So here's how we're going to grade the homework and the exams. So every single problem are going to be assigned 3 grades. So the first one is called identify, that's 30%. The second one is formulate, that's 40%. And the last one is the final solution, and that's 30%. So the first part, you will get a grade 1 to 4 for each one of them. So what's identify? It's basically saying what's required. What's given and what's required. Given in the problem this and this and this, and he wants us to calculate this and this and this. In the final exam, so many people lose points because they don't write what's given and what's required. So many people also lose points because they forget what is required. I mean, it's written in front of them, but in the rush of like, let's solve, they just see the first thing, I'll calculate the efficiency here, and they didn't see calculate the efficiency and check if the temperature will match, if the pressure is whatever. So when you give yourself a chance, you give yourself a chance to say what is given and what's required. This will allow you not to miss the solution. Okay. Another thing that people lose points over, and it just doesn't happen just for students, it actually happens in professional life, okay, is units. So people will mess up the units. They use meter instead of, they use kilometer instead of meter, they use pound force instead of slugs. They use degree C and they should have used Kelvin. They use PSI and they should have used pound per square foot. So all those conversion units, the place to do them is given. When you say what's given in the problem, and you say P1 is, you said 20 kilopascal. No, you would say 20 10 to the power 3 Pascal. And you said the temperature is 40 degrees C. And you know in the back of your head that you are probably going to use B equal rho RT. And that T needs to be in Kelvin, right? So here he said 40 degrees C. You don't write 40 degrees C, you write 40 plus 273 Kelvin. So that given section, think of it as a place where you convert what's given in the problem to the right unit that you're going to use later on. Okay, I promise you this will save you at one point. Okay, and I remember very clearly 1 year, I don't get bored for telling this story because it was so amazing to me. So 1 year I think it was probably a compressible flow course or something when I was undergrad. And that guy was like, the professor was giving us B1 and B2 And we're going to use the isentropic relation. You know how say for a compressor, you go from 1 to 2s. This is again the TS diagram. And you say, he would say find T2, right? Find T2. And you know that the solution would be, you know, P over P is T over T to power, you know, gamma over gamma minus 1 and stuff. And I know that all I need is just the ratio, right? So when I was reading the problem and I was telling myself, you know that we just need the ratio. It doesn't matter whether you're going to do it in kilopascal or Pascal. And then the other side of my head say, well, we know, but we have to stick to SI. Let's just write Pascal. And then when it comes to the issue, I'm writing this, and then I'm saying, well, 80 times 20 and 10 to the power 3. And why you're doing this? You know that it will cancel. Doesn't matter. And the other side of my head say, shut up. We said we're going to stick to SI. I'm going to stick to SI. Just let me finish. And then I'm pulling my calculator to calculate. And I remember this clearly because it was so, like, it took a lot of my time when I'm doing the exam. And they're like, 80 times, and then seriously, are you gonna now multiply by 1,000 and divide over 1,000? Did you totally lost your mind? And like, okay, I'm not gonna do it, but just to know, you know, but I'm gonna cancel it over here. But that story told me basically after the exam, like, wow, I am really committed to using SI. The time that I spent arguing with myself, you know, whether I should use kilopascal or not, that means that someone is like really inside here worried about SI units. So I hope you get a little bit paranoid about units, because a lot of people, that the story that I hear is that the Lockheed Martin and NASA, they were like in one of the first Mars rover landing. And I hear that story in the AIAA conference, the American Institute for Aeronautics and Astronautics. And the guy said that they basically give them the thrust in bound force, and NASA thought that the thrust should be in Newton. And so that kind of like missed the calculation of the landing. So now whether that story is correct or not, I'm not really sure, but it should really scare us that, you know, people could have serious problem if not saying the right unit or using the right unit. So anyway, personally, when I was a student, I loved doing this, and I didn't get points for it. When I was a student, there was no point for doing this, but this helped me to calm down. You will be surprised. I was a really good student, but every single exam I remember taking, the first time I always see the exam, I always panic and I tell myself, man, I'm gonna fail that exam. This is super hard. I've never seen those problems before. And I get so nervous, but when I start writing what's given and take the time to decipher the problem and what's required, it kind of calmed me down, and I can, and especially this part. And that I'm not alone in this. A lot of engineer research show that engineering students, compared to other students in the university, they understand figures. We are good. If you are engineering students, you understand figures. Like you can just making that sketch make you realize is going up. This is isentropic. There is a relation between those pressure and temperature. Or just like writing the sketch, you know, QH and W and QL, your eye is basically telling you, this guy divided into two. I bet the first law is saying QH is QL plus W. Point is, just writing what's given and what's required and making a sketch for yourself is guaranteed to calm you down and almost show you the way to solve the problem. Because again, engineering students think in pictures. That's why we are good with equation and charts and figures and circuits drawing, and right? We feel comfortable with this. And in this course, you will be rewarded for doing that. because you will get 30% of your grade of do this. Okay, so 30% just saying what is given and what's required. The formulation bar, that's basically writing the equation. They have the correct equation, you get 40%. Now, the last 30% is to actually come up with the right number, right answer. So if you said the solution is 30, but you didn't write 30 kilonewton, you are not going to get 4, you're going to get 3. So units not there, you'll get 3. Number is slightly wrong, you will get 3. Number is totally wrong, you will get 2. No number, you will get 1. So you can see that even if you don't do anything except saying what's required and what's given, and you leave the problem, you get 4, 1, and 1. Which I know that eventually translate into a D, but I mean, what do you expect? You don't, if you, every single problem you just write what's given and what's required, what does that say about you? Let's say you know English language, basically, right? So, but you need to get a D so that when you leave, we tell whoever hire you, well, this guy, you can talk to him, he can understand you, but he does not know anything, basically. He cannot solve anything, right? Because he's always getting 4, 1, and 1. So that's fair. And if you miss the final answer, always, for whatever reason, you don't know how to use a calculator, you are cursed, you don't just, like, there's a curse that will prevent you from getting any good and correct answer, you are not going to get an E, you get a B. And that's also fair, because we need to tell the people that engineer, he know how to do things, but he will never give you the correct answer. If you ask him anything, he will always tell you the wrong number. So they need to know this and assign someone to always check your calculation, right? So I think the system is pretty clear, and I think you'll find that it's actually super easy to comply with. Questions so far? All right, I'm gonna take another 5 minutes break to fix my mask because it's masking my glasses. So 5 minutes more break. Okay.